Okay. Thanks for the introducing, and thanks for you to come to my talk. I'm Zhongyi Ni, a PhD student from the Hong Kong University of Science and Technology, Guangzhou. Today I'm going to introduce my Julia package, TensorQEC, which is a quantum error correction package based on tensor networks. This work is done with my advisor, Professor JinGuo Liu. Okay. For today's talk, I'm going to introduce the basic ideas of the quantum error correction first, and then I'll show how we infer the Pauli errors with tensor networks, and after that, I will introduce how we use tensor networks to simulate coherent errors. There is already a Julia quantum error correction package called Quantum Clifford, which includes Clifford circuits, graph states, and other quantum stabilizer formalism tools. So why do we need TensorQEC? The main reason is that their simulation of Clifford circuits is mainly based on the tableaux method, which doesn't work for a non-Clifford circuit. And also, we use tensor networks to inference errors, and our package is very compatible with YAO. Okay. So what is a quantum error correction? A quantum error correction code is usually defined by a set of Pauli strings called stabilizers. For example, here we have S1, S2, and S minus K are stabilizers. Inside this circle is a eigenstates to S1 with eigenvalue 1, and inside this circle are eigenstates to S2 with eigenvalue 1, and so on. The intersection of these circles is a coding space. We encode our quantum state from a larger Hilbert space into this coding space, and we measure the stabilizers frequently to check that. If the measurement outcome are all 1, then we know this quantum state is surely inside this coding space. If not, we can infer the error with measurement outcomes and correct it. Okay. The whole quantum error correction procedure is shown here. We first encode our data qubit with some ancilla qubits into the logical state, and then some error may happen. Then we extract the syndrome into some other ancilla qubits and measure them. Based on the measurement outcome, we can infer where and what type of error it is actually happened, and by applying the inverse of this error, we can correct it. We may repeat this measurement and correction procedure for several times during the whole quantum computation process. Finally, we can decode the logical state and measure them to get the computation outcomes. Okay, here we take string code as an example. We use 7 data qubits, those white dots, encode 1 logical qubit. We have 6 stabilizers, x1, 3, 5, 7, x2, 3, 6, 7, x4, 5, 6, 7, and also z-type, z1, 3, 5, 7, and so on. In TensorQEC, we can define a string code instance with this string code and get stabilizers of it by stabilizers. Here we can see we get x1, 3, 5, 7, x2, 3, 6, 7, and so on. This function here encodes stabilizers, takes the stabilizers, and outputs the encoding circuit for this string code. We can visualize this circuit by this circuit in YAO. This data position records where the data qubits we put, and the rest qubits are initialized in the 0 state. And this bimatrix here records more encoding information, and we may use it later. Also, we can generate the measurement circuit with this function. It takes the stabilizers. Stabilizers 4 to 6 are these stabilizers. Here we only generate the measurement circuit for these stabilizers. Here we get the measurement circuit and the position where the stabilizers are measured to, 15 to 17. We can visualize this circuit. The first 7 qubits are data qubits, and we just encode our data in. And then we first copy the error into some ancilla qubits and measure the stabilizers on it. This qubits 15 measures the stabilizer Z1357, and this qubit 16 measures the stabilizer 2367, and the last one. Okay, let's see what will happen if there's a poly error happen in this circuit. For example, we have an X error happen on the 6th qubit. To see how this error propagating through this quantum circuit, we first define this error as a polystring. There's 17 qubits in total. The 6th position is this X, and this Clifford simulate function show us how this simulate how this polystring propagating through this measurement circuit. The rest dot output is the final polystring. Also, this structure rest records all the history of this propagating, so we can generate the history in this figures folder, and we draw a GIF with those pictures. As you can see, this X here is propagating through this circuit. Okay, and okay. First, we copy this error from here to here, and then we measure the stabilizers. Since poly X and poly Z are anti-commute to each other, so the Z stabilizers contains this error qubit 6 will be flipped, and the rest stabilizers will stay the same. The first stabilizer, Z1357, stays the same, and the other two, 2367 and 4567, contain 6. So they are flipped. After this circuit, we measure the last 3 qubits to get the syndrome of the stabilizers. We will get a syndrome 1 minus 1 minus 1 here, and then we know there's an error happened on the 6th qubit. Take another example. If the measurement outcome is 1 1 minus 1, then we will know the qubit 1357 and the 2367 are there's no error on them, so the error is on the qubit 4. Okay, generally this is an inference problem. We have the measurement outcome of some of the stabilizers, and we also have a prior error rate on the physical qubits. We need to infer what error is actually happen on the physical qubits. The most intuitive way for this problem is to make a truth table. Here we can make a truth table with make table, and it takes the stabilizers, and the 1 here means this table only contains single qubit errors, since Sting code is only capable of correcting single qubit error. Again, you can see if the last 2 stabilizers are errored, the Z2367, Z4567 are errored, then we know there's an X Liu error happened. Okay. However, to make a truth table for large code, the truth table may be significantly large, and also it doesn't contain any prior error rate in it. So here I will introduce how we use tensor network to inference the error. First, this inference problem is actually an MMAP problem, which means that we have some evidence on some variables. We have some variables to be marginalized, and the distribution on the rest of variables we actually want to infer. The evidence is the measurement outcome of the stabilizers. The variables to be marginalized is the intermediate state during in the circuit, and distribution we want to infer is error distribution on the physical qubits. Okay, and to solve this MMAP problem, we first transfer this quantum circuit into a tensor network and use this Julia package tensor inference.jl to solve this probabilistic problem. Okay. Okay. Now we use YAO to simulate a real physical device and perform quantum error correction procedure on it, and use our package to infer what error is actually happen. First, we generate a random single qubit state data and place it on the data position. The other qubits are initialized in 0 state. That's our initial state. Then we apply the encoding circuit here to encode this initial state to the logical state. Then we manually apply an X6 on the 6th qubit to simulate there's an poly X error happened on the 6th qubit. Then we can measure the stabilizers on the logical state. The stabilizers, the first 4 stabilizers, first 3 are X stabilizers, and the fourth is Z1357 stays the same, and the last 2 stabilizers are flipped. That's a measurement outcome. Also, we need to define the prior probability for each physical qubit. Here, we mean there's 85% of probability that this physical qubit stays, there's no error on it, and 5% of probability that there's an X or Y or V error on it, respectively. Okay, we put our measurement outcome, the bimatrix, the encoding circuit, and the prior probability into this function inference. We get the error polystring, which is exactly the X6 we applied on it. By applying the inverse of it, we can correct this error, and then we measure the stabilizers. It will become all 1 now. Also, we can decode this logical state and check the fidelity between it and the original one. Okay. Besides random poly error, there's another type of error called coherent error. A random poly error is that there's a classical possibility that the qubit is flipped or not, which is usually caused by the environment noise of the physical device. For coherent error, it is usually caused by inaccurate operations. For example, we use maybe laser beams to apply an X gate on a single qubit, which is a rotation around the x-axis, right? And maybe the laser is not long enough, or the amplitude is not correct. The rotation angle or the rotation axis may be slightly different from the ideal one. So the outcome may be not exactly this direction. That's a coherent error. For random poly error, we have Clifford circuit simulation to simulate it effectively. And there's a threshold theorem told us that if the error rate is below a certain value, we can use a large enough code to correct it. However, coherent error gates are no longer Clifford gates, making it difficult to simulate. And also, we don't know whether the threshold theorem holds for this coherent error. Here, I will introduce how we use tensor networks to simulate a coherent error quantum circuit. Actually, any quantum circuit can be simulated with tensor networks. Since quantum states are vectors and unitaries are matrices, they are all tensors, right? And we can connect a quantum state and a unitary to get the final state psi prime. And also for density matrix, it works like the same. Okay. We believe that in some situations, tensor network is an efficient representation of quantum states and an efficient simulation of quantum dynamics. However, for highly entangled states or deep circuits, there may be no advantage. Okay. In our package, we first define the stabilizers and the encoding circuits as before. And we construct a circuit with Yao. Here we first encode the initial state into the logical state, and then we apply a logical X gate, which consists of 7 X gates on all qubits. Then we decode the state with the encoding circuit. Now the data qubit is applied an X gate on it, so we apply this X gate back to recover the initial state. This circuit is not an identity circuit to all qubits, but it should act trivially on the data qubit. To check this, we need to partial trace the amphilia qubits out, which is simply done by connect the subsystem the indices of the subsystem that we want to partial trace out together. So the tensor network representation of the previous circuit acts on the density matrix of the data qubit look like this. We initialize the amphilia qubits in 0 state and partial trace them out after the circuit. And if we contract this tensor network, we got tensor looks like this. Okay, in our package, we can transfer a quantum circuit into a tensor network with this function simulation tensor network. Also, we need to specify which qubits are data qubits and which qubits are ancilla qubits that we want to trace them out. Okay, the input indices are 6 and 13. The output indices are 50 and 86. Okay. Then we use one-more ensem to optimize the contraction order of this tensor network, and then we contract it. As you can see, it is surely an identity tensor because only 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 1, 2, and 2, 2, 2, 2 elements of this tensor is 1, and the rest elements are all 0. Right. Also, we can connect the indices of this quantum channel to compute the fidelity between this quantum channel and identity channel. We can use this function to get the tensor network looks like that, and optimize the contraction order, and finally contract it. We can compute the infidelity of it, which is very close to 0. Okay. Now we add some coherent error in it. This function add coherent error to each quantum gate in the quantum circuit. For example, the first quantum gate in the circuit is a Hadamard gate. And after add some coherent error in it, it looks like slightly different from the original one. Also, there's a face. Okay. Still, we can transfer this errored quantum circuit into a tensor network and optimize the contraction order and compute the infidelity, which is much larger than the previous one, because there's some coherent error in the circuit, right? Okay. Too fast. For summary, we first infer the polyarrow with tensor networks, and we also use tensor network to simulate coherent errors. And our package also include other basic QEC tools, like the construction of stabilizers, the construction of encoding circuit and the measurement circuit, and the simulation of Clifford circuits. Again, thanks to my advisor, Professor JinGuo Liu. Thanks for listening. Oh, okay. Do we do anything with microphones?
Yeah, please use the mic, so that way the screen picks it up.
Thank you for the talk. This is a really interesting tool that I'm pretty sure I'll be using soon. I have a couple of questions. First, maybe more on the technical side. What are the backends for simulating this? Like, do you have your own tensor network simulator? Do you use iTensor? Same for the Clifford simulators? Sorry?
One more answer. Is another Julia package. One more answer.
That's an independent package. Or is it part of your distribution?
Oh, it's an independent package.
Thank you.
Yeah, I agree. This was very interesting. I'm kind of curious just maybe about some of these coherent error simulations and how you might play with some of your inference tools in conjunction with those types of simulations. Do these things talk to each other in a reasonable way? Could I explore basically projection of these error sources onto the kind of like standard poly air channel models or things like this using your tools?
Actually, we definitely can use this inference tools to inference a coherent error. There still may need some work.
If it's okay, can I then to follow on, and I assume it's also relatively straightforward, maybe in the current interface, if I wanted to like specify my own, so you added a coherent error that was like unique for the whole circuit, but could I like specify individual gates having specific error models or something like this?
Oh yes, we have other interfaces, like if we want to replace every X gate with the same coherent error X gate. Like this.
Okay, and then yeah, that's interesting then. Yeah. Okay.
Thank you.
Thanks. I agree. A really nice talk. Is this package mainly for, so to speak, one-dimensional architecture, or also for like a two-dimensional system when you have, like, could you build, I don't know, an IBM architecture or something similar with it?
Qubit, you mean?
Yes, just anything like a two-dimensional system where you have like many connections between different qubits and gates on top of that.
It's mainly based on the stabilizer formalism, which I believe only works for qubits now.
Thanks. Thanks again. We're running out of time, and maybe we'll have the next talk. Is it Aaron about pickle? Am I correct? Pronouncing correctly?